On June 21st, 2023, an extremely volatile atmosphere was cooking over the Texas Panhandle. While the severe weather threat seemed rather conditional the morning of, by day's end, a small town 60 miles northeast of Lubbock, Texas, would become the focus of the weather world. My name is Ethan Moriarty. I'm a mechanical engineer by training with a fascination in tornado damage forensics engineering. This is a damage analysis of the Matador Texas preliminary EF3 tornado. Hello and welcome back to the damage analysis series here on the June 1st YouTube channel. If this is your first time joining us, this is a series where we look at tornadoes and their damage that they cause from an engineering perspective in order to break down what's really happening in these tragic storms. Today's case study is a very recent one. At the time of recording this video, the Matador tornado had only taken place a week ago, so all the information here is still preliminary, and there have been a number of folks and families that have been affected with the fatalities and injuries that have taken place. So I always want to be sensitive when it comes to taking a look and analyzing the damage of recent tornadoes. Rolling Fork was a particularly tough one to review, and this is no different. There hasn't been a lot of time for healing, so if you're watching this and you're from the Matador area, my heart is with you folks, and I hope that you guys recover in a timely fashion, and just know that you're being loved and there's a strong support system around you. I want to preface that a lot of things are subject to change here, but in the eyes of the weather world, when this first came out and on social media, there was a lot of controversy behind the preliminary EF3 rating. So we're going to break it down here from an engineering perspective in order to get an understanding of why it earned the rating that it did, at least in the preliminary results of the survey. Before we get into the damage analysis itself, we first must go over some of the statistics from this tornado as well as the weather background story. This tornado was on the ground for 9.4 miles over the course of 18 minutes. While this wasn't a long-track tornado that we're typically used to here in the damage analysis series, it still packed a punch and impacted lives, as there were 4 confirmed fatalities and over a dozen injuries at the time of recording this video. Once again, this is preliminary information, so a lot of this is subject to change. The official preliminary rating from the National Weather Service office in Lubbock, Texas, as well as consulting from the National Wind Institute at Texas Tech, as well as engineers like Tim Marshall that took part in the survey, this tornado earned a preliminary, emphasis on preliminary, EF3 rating with peak wind speeds of 165 miles per hour, so at the very top end of the EF3 threshold, just about to cross into that EF4 category. Diving into the weather side of the equation, it was an interesting day from the start, as it wasn't a super large synoptic pattern that we are used to seeing when it comes to violent tornadoes. It was a very conditional day. In the eyes of the Storm Prediction Center, the morning of the 21st seemed to have more questions than answers. East of the dry line in the Texas Panhandle, dew points were reaching well above 70 degrees Fahrenheit, so there was plenty of moisture at the surface level. Very steep lapse rates existed above the cap in the early morning sounding, which had already yielded results of CAPE well in excess of 5,000 joules per kilogram. While there was upper level wind support aloft, it wasn't the strongest, and it wasn't the typical digging trough that we see when we think of traditional high impact tornadoes. It seemed like in this case, the CAPE was kind of the driving factor of the day, as by the afternoon hours it had reached close to 7,000 joules per kilogram, so it compensated for the modest flow aloft. I must also preface that, once again, I am not a meteorologist, I'm an engineer, so take the meteorological things that I say with a grain of salt, but I've looked at severe weather enough to get the big picture idea, but that's kind of my personal impression on what allowed this event to be historic for Matador, Texas. By midday, the Storm Prediction Center had seen enough to warrant the upgrade in risk category, bumping up to an enhanced risk and going from a 0 tornado probability to a 5% tornado probability for the Eastern Panhandle. While there wasn't a main forcing mechanism in play here, it seemed that some of the terrain features that we have seen in the Texas Panhandle region, most notably the Cap Rock, probably was responsible for the dryline bulge and the circulations that occurred there that allowed for the initiation of the storm east of Amarillo. There was a tornado watch issued for the region around 3 p.m., and that initial storm that did fire near Amarillo initiated around 5 p.m. local time. The storm then began to propagate southward, moving from the north to the south, with multiple storm mergers taking place before the Matador tornado was ultimately spawned. Now that we've gone over the statistics and the weather story when it comes to the Matador tornado, let's dive into the damage analysis. Here we are zoomed into the survey of the tornado path, which was conducted by the National Weather Service office in Lubbock. And like I said as well, there was consultation from the National Wind Institute, from the local Texas Tech, and then of course other engineering experts on site as well. And the first thing to note here is the orientation of the storm track. As mentioned earlier, the parent storm was moving north to south and the tornado followed suit. The tornado touched down east of White Flat and then crossed over the river there and eventually worked its way down towards Matador, dissipating not long after Matador. So the tornado was on the ground for a little bit of time before actually reaching Matador. And as we zoom into Matador itself, one thing that I can't help but notice is the fact that it just skirted the west side of town, missing the main population center by only a quarter to half mile, I would say. And though this event is already tragic as it is, we could have seen a lot greater loss of life had that track jogged a little bit more east, or if there was some sort of occlusion that took place, curving that tornado into the town. So all things considered here, this could have been a much worse tornado, especially given some of the imagery that we have seen coming out of Matador, particularly with vehicles. We're going to start off with the first damage indicator, which right off the bat is an EF3. And this EF3 damage indicator was rated at 165 miles per hour. I think the important thing to mention about this first damage indicator is that the surveyors noted that the family rode out the tornado in the basement. They made it to their underground basement, and while none of the walls survived and there was debris that fell into the basement, no injuries were reported at this location, so nothing that was significant, which is a great thing to hear, that the folks of this household heaved warnings and made it to an adequate shelter in this violent tornado. The immediate thing that jumps out to me with this house, and this is a common theme that I've seen in this damage track that we'll dive into a little bit more, is that there is no, from what I can see in the images provided, no sort of retention features on the outer walls that contained the structure down in tensile loads. So what I mean by that is no retention to the foundation, which, in these tornadic events, if you want to have the structure survive up to a greater threshold of wind speed, you need those types of retention methods in order to help the house survive longer. So that's why, a lot of these structures that we've seen are capped out at EF3, because there wasn't those retention methods present in the construction of these houses. And that's just the nature of some of these buildings that are in rural West Texas and other parts of the country as well. Some of these building standards are a little bit more laxed. So, you're going to build cheaper houses. Builders are going to cut corners a little bit here and there in order to, save money on their end and on the buyer's end as well. So it kind of, it's It's a tricky situation to be in because, nobody really expects that their house is ever going to be hit by a tornado. But in those moments, especially if you don't have a basement and you're sheltering in an inner room, some of those retention methods are going to be a matter of life and death. So it's a little bit alarming to see that as a common theme across this tornado path. And frankly, not just this tornado, but many tornadoes that we've seen in history. So it's not a common theme that we're uncovering here with the Matador tornado. We move down the road a little bit to the next EF3 damage indicator. This one's slightly less than the previous. The main thing to note with this one is that there were some interior walls still standing here. But once again, once we get the close-up imagery between the outer walls and the foundation, doesn't look like there's much in terms of retention between those interfaces, and especially nothing holding it to the foundation. This also might be another instance of a, CMU block foundation. Just looking here at the floor joists here, and it looks like there's like an air gap underneath there. So, this house might have not had the best foundation in terms of, really anchoring the structure down above, the flooring and all that. As we continue moving down here, we reach this unknown damage indicator, which is one of the vehicles that we've seen. This is an important thing I need to bring up, is that in the current EF scale definition, there is not a damage indicator for passenger vehicles or anything along those lines. I think the original intention of the EF scale is that you have stationary grounded things that are not moving relative to the tornado, and once you introduce that extra variable, which we're seeing a lot of in the Matador tornado, obviously there's the imagery that's come out of engines ripped out of vehicles and stuff along those lines. The tough thing with those is that, obviously the vehicle's been thrown, so it's a violent tornado, but it's really tough to start estimating wind speeds with an object that's moving with the tornado. You're not stationarily relative to the tornado. So that it really complicates things. I know that in the next iteration of the EF scale that is in works, that damage indicator category is going to be added. There's probably a whole multitude of things that we've gained in understanding since the enhanced Fujita scale was implemented in 2007 to now. Obviously, 16 years is a lot of time that we've seen technology advance, so our understanding is getting better and better. So the problem is that we can't really go outside of the confines of the scale as it is right now, due to the matter that if you start making exceptions with cases now, you start calling into question the validity of previous cases. If you look at El Reno 2013, for example, an EF3 rated tornado that we obviously know had EF5 intensity, but it just didn't hit the structures needed to verify EF5 level damage. Yet we had mobile radar measurements, for example. If you start taking that into account, then you're no longer a purely damage-based scale that the EF scale is, and it starts calling into question the rest of the tornado ratings, and now you're no longer consistent. And that's the thing with standards like this. You kind of have to stay consistent, even if they are limiting the actual classification of the tornado. So while those things are going to be addressed in the next iteration of the scale, we're not at that point yet, so we still have to use the EF scale in order to rate tornadoes commonly across the board, as unfortunate as it is, if you really want, the true power of the tornado to be rated, right? So it's, a give and take in that respect. But nonetheless, let's dive into this vehicle unknown damage indicator real quick. It was noted in this survey that the vehicle was thrown from the road. Just measuring out the distances on Google Earth here, the vehicle was found 100 feet from the road directly, though it looks like that it came from north to south with the direction of the tornado, and so it probably traveled more than 100 feet from the road. There wasn't any notes of any injuries or fatalities that were with this vehicle, so I'm not really sure if this vehicle was being driven or if it was just parked along the side of the road there, or if it came from a completely different location. I'm not quite sure. They didn't note any injuries or fatalities within the damage indicator, but just looking on the damage here, this doesn't look like a survivable accident. I talked with a very close family relative of mine that does vehicle reconstruction, and I asked about this damage indicator, and they said if they were investigating this crash, this was probably not a survivable crash. So something to keep in mind here as we move along here. Moving to our next unknown damage indicator, this is another vehicle one, and this one is quite alarming to see. So this looks like to be I think it's either a Cadillac Escalade or a Chevy Suburban, large SUV type vehicle. And the big thing to note here is pretty obvious. In that rear passenger door there is a metal pole that is barbecued, skewered right through it. And I tried really hard to do some sort of calculation in order to support how fast that pole needed to be moving in order to penetrate the door. But the further I got into it, the more assumptions and stuff I had to start taking into account, to the point where it was completely unrealistic to do a simplified mathematical model that we can just kind of do by hand and have it still be reasonably accurate. So ultimately, if we were to do this and analyze it, it would come down to a couple of things. The first thing we could do is do empirical evidence testing. Obviously, if you shoot a metal pole into the thing with a giant air cannon or something like that, you would get a pretty clear answer pretty quickly just from testing data. Or you could do a finite element analysis, which is basically a computer model, and set all the parameters up, build a 3D model of the vehicle, 3D model of the pole, and then set all your conditions and constraints and let the computer do all the math. Because what it does is it basically breaks all of the little door elements and the elements of the pole and basically puts them all into little nodes, and then at each node it calculates all the material properties as it's undergoing, stresses and all that type of things, and then you get a pretty accurate model in order to see where the failure point is. Unfortunately, programs that do that are extremely expensive and usually require like company licenses and stuff like that. So I don't have access to an FEA software just off the top of my computer here, and also it requires great computing power that my current setup would not support. So I tried to get some sort of answer at the bottom of this, but at the end of the day, I think the main point to get away here, though we can't get a definitive number at what speed this would occur at, I think it goes to show that you really shouldn't be sheltering in vehicles. If we saw the last vehicle, we're looking at this vehicle, not only the fact that your vehicle can get tossed and mangled from that perspective, we're talking about fast-moving, wind-borne debris that's penetrating vehicles. Obviously, we can go back to our good friend, the kinetic energy equation. We've talked about it a lot on this channel here. That velocity term is the killer term. The faster you're going, you're exponentially increasing the amount of energy that object possesses. So, once again, don't shelter in vehicles when it comes to a tornado. Moving down from that Escalade, we're going to the next structure that was impacted, which was also rated as an EF3, fully slabbed house. It was a masonry type house from the looks of it, masonry exterior. One thing to note about this damage indicator was that there were reported injuries at this location. From the sounds of it, it was the residents who were trying to get to their basement when the tornado was about to impact their house, and the walls started to come down around them. Obviously, if you're living in Western Texas, you get tornado warnings fairly often, probably a couple times a year even. And, you get this kind of cry wolf effect where you get a tornado warning, nothing happens. You get a tornado warning, nothing happens. But when something does happen and you've gotten used to stuff not happening, you let your guard up a little bit. You're not going to your safe place right as the tornado warning's issued. When things start to go bad, they go bad very quickly. And I'm guessing that things started to go bad very quickly for these folks, and they weren't able to get to their basement in time, and they ultimately were injured in the process, which is really unfortunate to see. And I think it just drives home the point that, whether or not they were, actively heaving the warning and it just took time for them to get down to their basement or something along the lines of that. I don't want to put judgment on these folks, but I think it's just an important message that the moment there's a tornado warning issued, you should be acting on your safe plan, get to your safe space. This tornado was obviously on the ground for several minutes, given that the tornado didn't impact the town of Matador until the end of its life, basically. So, you had time to act upon your plan. It's important that when you have that tornado warning out, act on your safe plan and get to your safe space. Unfortunately, with this damage indicator, there were no clear images of the foundation. I'm gonna assume that because it was rated at EF3 165, that there probably wasn't the retention methods needed in order to verify higher than that. That's just my assumption. Obviously, I wasn't there surveying. I hope to get a couple of actual tornado surveys under my belt one of these days as I dive more and more into this. But I think the message of being able to get to your safe space in adequate amount of time is the important message that we can gather from here. Popping over to the EF2 damage indicator that was just to the east of that EF3 damage indicator. Here with this EF2 damage indicator, it's another masonry type structure, and as we can see, it was impaled by, construction material. Looks like a 2x6 there in this case. Roof is mostly still intact there. I think the actual survey DI noted that there was roof damage of significant extent. That's why I earned the EF2 rating. And the windows are blown out along that eastern side. But I think this structure fared a little better than the one further west of it. Maybe because of some of the newer theories that are being tested and researched right now is that, kind of that eastern side of the tornado, if you think you have that counterclockwise motion, so your wind direction is going with the forward momentum of the tornado, so with the direction of the storm. So you almost get like a double vector kind of thing going on where you get this added velocity from the storm motion. And then along that western side, it's counteracting that storm motion. So you kind of get this little bit of competing, kind of drawing away a little bit. So there's research on how much that actually affects tornado wind speeds and stuff like that. I'm not sure if there's anything published at the moment, but I know there's stuff that's currently ongoing with respect to that question. So just something to think about as, these two damage indicators were on the same latitude. This one receiving an EF2 and looking a little bit more structurally intact, and obviously the EF3 that was further west. Once again, though, I wish we could have put together a more interesting model here in order to kind of estimate the impaling speed of that structure, because I feel as though that would be a very interesting thing to derive. We're coming down here to this EF3 damage indicator, and if you're looking here on the satellite imagery, you're like, there's nothing there. How can there be anything? And that's because at that EF3 damage indicator is a brand new Dollar General. Going into the Street View earlier, I went to the latest Street View imagery, which happened to be in December of 2021, and there was a mostly complete Dollar General there. They hadn't put up the sign yet. There were still construction vehicles in the parking lot there. It looks like they had just finished building the exterior of this building. But our current satellite imagery, or the most current satellite imagery from this close-up of the town was in 2016, so obviously we don't have that to go off of. But nonetheless, this was rated EF3 at 155, and there was a lot of uproar, not only in this tornado, in the Matador tornado, but also in the Rolling Fork tornado when it came to the Dollar General. It was another relatively new Dollar General that was built, and there was a lot of people saying, hey, this is a brand new structure, and it's only getting, an EF3, EF4 rating. What's the deal? And the thing with these like department store, or for lack of a better term, type of buildings, is that they're basically a giant metal box, and you have walls on all four sides, right? But very open in the middle, right? So if you have like a nice large wall, for example, that's taking your wind load, You're supported at the, with the girders and stuff and the metal supports and the I-beams and all that are kind of holding up this wall. But nonetheless, you still get this giant bending moment that's happening on that wall. So if you have a distributed load across the wall, we're looking down at like a cross section, right? You put a distributed load against that wall. You have the walls that are perpendicular to it that are kind of acting as your anchor points. But you still get this bending in there. No matter how many struts or supports you put along that wall, there's no perpendicular extra wall that's breaking up the bending moment that's building up in that wall. So it's eventually gonna cave in catastrophically. Once you have a small failure, it's gonna catastrophically fail. And it's important to note that the glass door and large glass front that is the entrance of this Dollar General is facing north. And as we know, this was a north to south moving tornado. It's already impacted structures at this point, so there's a lot of debris in the air. The moment one of those windows go, we know these windows aren't rated for the highest wind speeds by any means. So the structure is compromised. And, while some of the damage from the damage indicator looks quite impressive with some of the bent steel and some of the foundational bolts being kind of pulled out a bit, we have to keep in mind that these huge walls that are now being subjected to this wind load have a giant moment arm attached to them. So basically, think of these walls as giant levers as this structure is failing. That whole wall is being pulled down, and it's a huge surface area for the wind to act upon. So at the end of the day, you don't need a high wind speed if you have a huge platform area that's acting as this giant lever to pull on the foundational supports of the structure. So while it is a new structure, new construction doesn't necessarily mean quality of construction or it's going to be bulletproof, right? So especially in the case of these Dollar Generals that are, kind of these cookie cutter stores that they're throwing up all over the place. These builders are just trying to get these things up as fast as possible. So you get rushed construction factor into it as well. So there's all these factors that, even though it's this new structure, you're not necessarily going to be getting a high rating out of it if it's not designed to sustain high loads. And it's basically just a giant warehouse type structure at the end of the day. So, it's not built to survive wind loads that are in a violent tornado at the end of the day. So I think it's important too that this is another structure that you shouldn't be sheltering at, right? Big open area, large glass windows and stuff like that. Maybe if you sheltered in the bathroom, that might be your saving grace there. But, you would not want to be caught in the middle of a shopping aisle when this tornado is rolling through, that's for sure. Moving further east here, we have this EF2 damage indicator of a motel that had its roof ripped off. And the main primary failure point here was the uplift force that ripped that roof right off. And the big thing that I noticed when looking at the original structure in Street View is that there is a giant awning that is on the north side of the building. So with this north to south moving tornado, you get wind that's funneling underneath that awning. It's just going to peel back that roof like a soda can or something, or a tuna can. You get this like nice little handle for the wind to kind of funnel underneath and basically peel that structure off. Not only that, but there's also that big pressure drop that we always talk about when it comes to tornadoes. Tornadoes are giant low pressure centers. Basically, you have all this pressure that's atmospheric in the structure itself, and it doesn't have time to equalize to that much lower pressure. So you're going to get this giant uplift force on the roof as well. So there's that. You have a Bernoulli's principle type thing where you have the air going over top versus the stationary air inside. That causes a pressure difference. So there were a lot of factors that led to this structure just blowing its roof off. And the walls survived ultimately in this case, and maybe that pressure relief allowed the rest of the structure to survive. So just something I wanted to look at here, because I figured that awning was probably a big primary driver in the failure of the structure. Moving down here to another residential EF3 damage indicator, there was a fatality that occurred at this location. Around the structure, there were some heavily stripped mesquite trees, which are a hardwood. A lot of people, like to point to the mesquite trees and say, hey, these are a hardwood type of tree. They're getting debarked and stuff like that. While they weren't fully stripped and they weren't fully debarked, I think, we also have to consider that, there was a lot of debris in the air, a lot of sand and stuff like that. Western Texas, dry, arid climate, a lot of particulates in the air. So there's not a lot of research on debarking and stuff like that and what are the forces required. As much as I want to dive into that, because it's a big argument that a lot of people have when it comes to tornadoes, that and ground scouring. Those are the two things that I feel like I get a lot of comments on, and they're tough to quantify, and I want to be able to do more, but there just isn't the research out there that really supports how it happens and the forces at play. Maybe we'll get to a point where we can explore that more with the next EF scale. Maybe there is some research that I'm not aware of, but nonetheless, it's tough to say what causes debarking. I don't think a hardwood tree makes it harder to debark. I think it makes it harder to completely rip the tree out of the ground and stuff like that kind of thing. So I could be completely wrong there, but I think the reliance on trees is tough. I've never been the biggest fan of trees as damage indicators, to be completely honest, but nonetheless, some of the tree EF damage indicators that are in this tornado path, a lot of people criticized if they were lower ratings. I think the other thing is that the trees in this area are not all mesquite trees. There's also things like pinyon pine, which are a softwood. So, a lot of those things come into consideration. The crews that are out there doing the surveys, they're identifying the trees and stuff like that. So they're not going to misidentify a tree, and especially a mesquite tree. They're pretty distinct. Obviously they have that mesquite smell. So, I wouldn't think there would be an error when it comes to determining what type of tree it is, especially when if you found a significantly stripped tree that could verify, a much higher wind speed like a mesquite, you wouldn't misidentify it. So just something to talk about. But going back to this residence here, like I said, there was a fatality at this location. Another instance here of a possibly rotted foundation from what it looks like. There were some close-ups of the foundation here that looked rather questionable to me. So, even if there was retention methods, over time, you're going to get some degradation in your materials that you use to build the house. So that's something always to consider here. As we move further south here, we get down towards the end of the tornado path. There's this interesting unknown damage indicator of a giant 500-foot radio tower. It kind of fell in this funky fashion, and what it is believed to have happened is that there was, the guide wires that support it. One of those got severed by debris or something along those lines, and it kind of fell in this funky spiral. Just an interesting damage indicator that there isn't a standard DI to place it under. So I just thought it was really interesting, and it was cool that the survey team in Lubbock actually laid out the pattern in which it fell. I feel like it was a cool little thing to find that you don't normally typically see in some of these damage assessment toolkit exports. Finally, as we get down towards the end of the path here, there's a nice unknown damage indicator that has a June 1st analysis written all over it. It's a pretty simple street sign, nice platform area. We've seen a couple of analyses that I've done here in the past, these combined loading style analyses that we've done to kind of estimate at what point the sign would have failed at. So let's go through the math now, because it wouldn't be a June 1st damage analysis video without a little bit of math. After assuming all of the geometry here, we got a nice 4 by 3 foot sign. It's 7 feet off the ground, a standard height for road signs. We basically have to establish the material properties. So this pole is made from galvanized steel. It's clearly anchored sufficiently, and it was bent over. So we know that steel yielded and basically exceeded its elastic region. So we know that it exceeded its yield strength of 70,000 PSI, which is a typical yield strength value for galvanized steel. We dimension out our moment arms and find the coefficients of drag for both a flat plate, which is pretty standard at 1.28, and then an elongated cylinder. Cylinders have different coefficients of drag based on their length to diameter ratio. And in this case, it's a really long, skinny cylinder, and it comes out to around 0.95. A more stout cylinder might actually have a lower coefficient of drag, as it's able to kind of use those surfaces to kind of bleed off some of that force. So, interesting how coefficients of drag work when it comes to cylinders. We're going to use our stress due to a bending moment equation, which is mc over I. M is your sum of your moments. C is the distance out from the neutral axis of the bending. So, if you have like a cylinder that's way wider, way thicker pole, that distance is going to be a lot longer out, which kind of helps in your favor in order to prevent that bending motion from failing the structure. And then I is your area moment of inertia. That basically takes into account the shape of the object and how that is able to dissipate stress. Since we've established all of our geometries and material properties, the only outstanding variable is velocity. And we use our force of drag equations for both the cylinder portion and the big flat plate sign portion, and arrange everything in such a way so that V is the last variable, and then do a lot of algebra in order to get V on the other side of the equation and back solve for velocity. When we do that, we get a final answer of 169 feet per second, which is around 115 miles per hour, which makes a lot of sense here. It's a road sign, doesn't have the thickest pole or anything like that, so that sounded like a very reasonable value to me when it comes to the wind speed required to yield the bottom of that pole. With that includes the damage analysis of the Matador tornado, and I have a couple of closing thoughts when it comes to this tornado. First off is construction quality. That's something that we have to take into account here when it comes to any tornado. And in the case of this small West Texas town, there are a lot of construction practices that were both probably subpar, and also things like, degradation over time with some of the older structures and stuff like that. So it's those types of things that are going to prevent you from being able to rate the tornado higher. Obviously we have the vehicle damage indicators, but as we discussed earlier, we can't start making exceptions without invalidating previous tornadoes that have been rated in the scale. You kind of have to stay within the confines of the scale in order to keep everything uniform across the board. That's just how it works at this period in time. We're going to get to a point where we're going to advance the scale, but we can't start invalidating results of previous storms now. And that's a very important thing to really keep in mind here. But the important thing is construction quality and kind of the lack of measures in place that could prevent, structures from failing prematurely and causing fatalities. We saw, a home that had some structural deficiencies that failed that ultimately resulted in a fatality. And, if things were a little different, maybe if the structure had an interior room survive, we could be talking about a different story here. And it's those types of things that really bother me when we're looking at these damage indicators, that, it's more than just a number. It doesn't matter to me if it's an EF3, EF4, EF5. At the end of the day, when it comes to what the final rating on a DI is, it's the construction quality that we're seeing here and whether or not it was enough to save a life. And in this case, it was not. Another thing to note, that like we talked about earlier, passenger vehicles are not currently a part of the current EF scale, but that's something that to be added in the future. So that's something to look forward to, and hopefully it'll provide more insight on tornadoes that we see in the future and get a more accurate rating. And then of course, like mobile radar and all that fun stuff is going to be considered as well. But in the meantime, like I keep saying here, we have to stick with the current confines of the scale. And with all of that out of the way, I just want to say my heart goes out to the people of Matador in this difficult situation. There have been a number of tornadoes recently that have impacted communities in both Texas and Colorado. So it's been a very interesting June thus far when it comes to severe weather. Usually we associate June with photogenic tornadoes in the high plains, not impacting much, but we've had a number of, high impact tornadoes, Perryton, Texas, and in eastern Colorado as well. So it's been a very interesting month, and there's been a lot to talk about when it comes to tornadoes and tornado damage. So I hope that the Matador case here serves as a little bit of a learning lesson in some respects, and hopefully people start heaving warnings and those types of things, safe spaces and all that type of messaging that we try to put out there. So once again, to the people that have been affected by tornadoes, my heart goes out to you. It's not easy looking at these damage paths, knowing that there are injuries and fatalities that have taken place. Thank you so much for watching this damage analysis video. And as always, stay safe out there when it comes to severe weather.